All right, this is a continuation of the 1.3 notes from yesterday. We're going to talk about increasing and decreasing intervals. You guys should be comfortable with this already anyway, because you already know interval notation, using parentheses and brackets when you need to. So, first of all, increase this function right here that I have drawn. It is increasing as you move in from the left and hit this point right here. Increasing because when you read a graph, you always read a graph from left to right. So when you are coming in from the left, the graph is headed up. And then from this point over here to this point, we call this a constant. It's constant because it's not changing. It's not increasing, it's not decreasing, it's staying the same. And then, of course, after this point, it starts to decrease as we read the graph from left to right. Probably not a big deal. So an example of that, we have a curvy graph here, and I am asking you, when does the graph, when does it increase and when does it decrease? So this is the problem that I have noticed from years in the past. When you are talking about a graph increasing or decreasing, you always have to talk about it in terms of its x value. So you always have to be thinking about, as you're moving along the x-axis, what's happening to the graph. So in this case, if I am up here and I am heading down, do you see how as I am heading down on the graph, the x value keeps getting closer and closer and closer to 0. So I am starting way over here on the left, and as I am moving in, my graph is heading down, 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 down. Remember, this graph heads up infinitely far to the left. It's going to, down here, it's going to head down infinitely far to the right. But the x values start very, very negative, and the graph continues to decrease until you get to this x value right here, which is -1. Are you okay with that?
Yeah.
It's decreasing until you get to an x value of -1. So I have written here that it is decreasing from a negative infinity all the way up to a -1. Now, why do I not have a bracket after the -1?
Because it keeps going. Right?
Well, yeah, because it doesn't stop here at -1. It's kind of like a pause, and then it starts to head up again. So then the graph is increasing, starting with that x value of -1, and it increases, 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 until you get up here to a +3, an x value of a +3. So the graph is increasing again, parentheses around both, because those are like pauses in the graph. And then when you get to an x value of 3, the graph starts to head down again. It will go on infinitely far low. Therefore, it decreases starting at an x value of 3 and going infinitely far to the right. Questions? Easy enough?
Would it be a negative infinity or positive like it is right there? Because it's going down.
Okay, that's what you are looking at. He's asking right now, shouldn't this infinity symbol be a negative infinity? Remember, we are talking x values.
Oh.
So that means that, yes, the graph is heading down. So you might think it's heading in negative, the y value is heading into a negative infinity position. But I am talking about what happens to the x values. As this graph is going down, we're talking about the x values that are increasing far to the right, which is positive infinity. That's the only part of this that's confusing, is remembering keeping the difference between the x's and the y's. Okay? If I was asking for the y value, yes, you would say negative infinity, but I'm not. I'm asking for the x values. Okay?
All right.
All right. Relative mins and maxes. You guys should remember this a little bit from last year. I think last year we called them local minimums and local maximums. Same thing. It means exactly the same thing, just a new name for it. Relative mins and maxes are the highs and the lows of a graph. I have an example of a graph there. It has 2 maximums. It has 1 minimum. This point right here being a maximum. This one right here being a maximum. And then, of course, this point right here being a minimum. They're maximums when you hit the highest point of a curve. Minimums when you hit the lowest point of a curve. just a little side note here, I have written down the calculator steps for you to use if you are calculating a maximum or a minimum. Second trace, you go to 3 or 4 and it kind of walks you through. It tells you to guess the left bound, guess the right bound. The calculator does all the guessing for you. I think it will come back to you you did it last year. It should come back to you very quickly once you try the calculator steps.
Will our notes be available on our test?
Notes will not be available on test. There are some units where you will be able to use your notes, but they will be when we start getting into a lot more trig, like sine and cosine and tangent and what they mean and such. But initially, no, you do not get to use notes.
Sure.
Okay.
Like calculator sessions, 3 and 4.
3 or 4. If you go to second trace on your calculator, option 3 I think is to find a minimum, and option 4 would be what you would choose to find a maximum. I may have those backwards, but you'll see, when you get there, that if you're trying to locate a maximum, you go to one of them. If you're trying to find a minimum, you go to the other one. All right, are we ready to move on, you guys?
No.
No. I'm gonna just scroll down a little bit though. Even and odd functions. Are we okay? Can I do this, you guys?
Yeah.
All right, even and odd functions. All right, by definition, some functions are called even, some functions are called odd. If a function happens to be symmetric with the y-axis, you call it an even function. If it happens to be symmetric with respect to the origin, then you call it an odd function. And some of you will be very, very good at graphing something and looking at the graph and saying, oh, I recognize that it is symmetric with the y-axis, it's even. Some of you will be very good at looking at a graph, recognizing that it is symmetric with the origin, and be able to tell that it's odd. Others of you are not good with spatial relations, which is me. I am not good. I'm much better at algebra than I am at looking at something and being able to tell you whether or not it's symmetric. By the way, it isn't even or odd. It's neither if it is not symmetric with the y-axis or with the origin. So if you can look at a graph and recognize that it is, in fact, symmetric with the y-axis, you can tell me it's even. You don't have to do anything else. If you can tell me that it's symmetric with respect to the origin, it's odd. You don't have to do anything else. I will show you the algebra steps here in just a second. All right. Another little note here. I wrote with a star next to it. In order to graph an absolute value, you go to math on your calculator, you arrow to the right to number, and then you choose option number 1. That will, this 3 right here is just marking that we're on page 3 of the note. You don't need to look at that. I'll go to option number 1. Did I show you guys this the other day?
Yeah.
Okay. So those are the steps in case you need to get them down, because you will be asked about to graph absolute value, and knowing the steps obviously will just make it a lot easier. All right. Is this graph even or odd?
Odd.
This graph, the first one. Is it symmetric with the y-axis, or is it symmetric
Even.
with the origin?
It's even.
It's even, and the reason it's even is this is the y-axis. If I trace here the y-axis, you should notice that this parabola is mirrored on both sides of the y-axis. So if I were to fold this graph right along the y-axis, the right side of it would fall right on top of the left side. Does that make sense?
Yeah, you.
So it's symmetric with the y-axis. If it's symmetric with the y-axis, we call it even. Now this is the one that I always find a little bit more challenging. The second example here is odd, and the reason it's odd is because it's symmetric to the origin, so why? So this is what I do. I imagine taking this graph and spinning it. Spinning it 180 degrees, and if you can spin it 180 degrees and have the graph look exactly the same way as it did when it started, then the graph is symmetric with the origin. So this right here, this part of the graph, you just have to imagine that you spin it 180 degrees. So in other words, you are rotating it around 180 degrees. And if you did that, you would, and now my graph is probably not drawn perfectly, but you would end up with this part of the graph falling right on top of this part of the graph. And if you were to take this part of the graph and rotate it, continue to rotate it, it would fall right on top of this top right-hand corner part of the graph. So in other words, imagine having like putting a fastener right at the origin and taking this thing and just spinning it. And if you were to spin it, the graph would look exactly the same way as it did when it started. Can you visualize that?
Yep.
Yeah.
Then it is symmetric with the origin, which means then of course that it is an odd function. Odd function here, even function here. All right. This graph right here, I gave you an example of one that is not either even or odd. This graph right here is not symmetric to the y-axis. You also cannot spin it and have it look exactly the same way it did when it started. Therefore,
Neither.
it is not even, it is not odd. But I'm going to show you the algebra steps behind this, and then we can stop for the day. So even an odd test using algebra, and this is the part that I sometimes prefer to do because visualizing things sometimes is difficult. So, all right, even an odd test using algebra, a graph is even. It is even if when you replace the x's in your function with a negative x, when you replace the x's with a negative x, you get the original function back again. So it says if f of negative x gets you, this right here means the original function. You may even want to make a note of that. It is the original f of x. And I wrote it out here too. You get what you started with. You get the original function back again. When you replace the x with a negative x, it's even. And it's odd if when you replace the x with the opposite of x, you get the exact opposite of what you started with. So you replace the x in the function with negative x, and everything in your original function is exactly the opposite of what you started with. So if you had a positive, and it turns out to be negative, then it's the opposite of what you started with. And of course, I will show you some examples of that. All right, f of x. Let's say I give you a function 2x plus 1. We have to figure out, is it even or is it odd? Well, here's the check. According to my algebra stuffs up here, you need to replace the x value with the negative x. So don't just write down what I'm doing. Make sure you're kind of watching and listening to what's happening here too. I'm going to replace this x with a negative x. See, I inserted a negative x here. And then I just evaluate this function. What is 2 times negative x? Well, it's negative 2x. And then the 1 doesn't change. It stays a plus 1. So this is what I started with 2x plus 1. Did I end with 2x plus 1? You did not end with 2x plus 1. Do you have the exact opposite of what you started with? The exact opposite of what you would start, the opposite of this thing right here, the opposite of it would be negative 2x minus 1. No. Is it the opposite? Everything has to be the opposite. Is it the exact opposite? It is not the exact opposite. That's why we said no, it is not even or odd. It is not even or odd. Letter B, another example. Again, replace x with negative x and see what happens. So I'm going to take this function, x squared plus 5. I'm going to replace the x with a negative x. And I'm going to see what happens. So I put my negative x in where I had an x. Negative x squared is x squared. add 5 to it, you're going to get x squared plus 5. Is that what I started with? The function I started with was x squared plus 5. I ended with x squared plus 5. So I ended with exactly what I started with. Okay? Therefore, it is
Even.
even. One more example. Probably going to be an odd example.
Even.
F of x equals x cubed minus 2x. That's my function. So my check. I'm going to check to see, is it even or is it odd? So I'm going to replace x with negative x. So I put a negative x in here. But I also have to put a negative x in for the other x there. So twice you have to replace x's with negative x's. So negative x to the third power. That means, I'm going to do the math over here, negative x times negative x times negative x. Well, negative x times negative x is positive x squared. And then a positive x squared times a negative x is going to give you negative x to the third power. So negative x third to the third. And then here I am multiplying negative 2 times negative x, which is a positive 2x. So I started with x cubed, a positive x cubed minus 2x. I'm ending with negative x cubed and a positive 2x. Do I have exactly what I started with?
Nope.
Do I have the exact opposite of what I started with? Therefore, it is odd.